As promised, we will begin our exploration into manufacturing statistics with an industry-relevant, though hypothetical case study: TV brackets on demand. Suppose you are a manufacturing engineer for a consumer electronics company. Imagine the following scenario. Global sales of television sets have seen a significant uptick in demand. Recent forecasts and sales tracking data indicate TV revenue will grow by 9% to $26 billion within 2 years. Worldwide TV unit shipments increased by 30% last year alone, and in the United States, television set unit sell-through numbers at retail rose a whopping 86% to 1.1 million for the last week of the first quarter alone, beating out other tech categories, many of which are also enjoying a post-pandemic demand spike. Rapid growth in this space has led to an increasing number of TV models with new features and functions. One trendy offering driving sales is digital art apps. These units allow weekly subscriptions to personalized, ultra-high-definition, museum-quality art pieces. When not binging on the latest comedy drama series or playoff series, homeowners enjoy their own digitized den of Picassos, Remingtons, and Rembrandts. Some consumers even mount the TV within a decorative design frame, so that the sets are almost undistinguishable from traditionally framed visual artwork when in art exhibit mode. The downside of this otherwise positive trend is that 90% of customers still opt for do-it-yourself, at-home TV installation, and more than half of the installations have problems. In fact, customer complaints are on the rise, with customer satisfaction ratings dipping despite the novel features. Worse, a record number of potentially damaged products are being returned post-DIY install, and these scratch and dent units must be resold with deep discounts, driving down profits by as much as 18%. One issue is that TV manufacturers have not agreed on a standard mounting method. While slimming down the profile of modern advanced TVs, some companies have created proprietary brackets in non-standard hole patterns. A traditional hinged bracket design is the existing product that fits many pre-existing units. Imagine a scenario in which your company is unable to stock the large variety of mounting brackets and it's experimenting with a new on-demand bracket fabrication in a lights-out fully automated factory. A sleek mobile app allows selection and customization of mounting hardware, which is fabricated and shipped to the home within 24 hours. There are options for different materials and bracket patterns, which are precision cut with a water jet. The three-stage process involves mobile app ordering, on-demand fabrication, and express shipping of customized TV brackets. Imagine if your task is to optimize shipping. To improve both customer satisfaction and profit, after boxes roll off the assembly line, the custom fabricated mounting brackets must be shipped efficiently. They must arrive in the fastest time with the lowest cost. A data-driven decision-making process must be employed to select a factory-to-home shipping carrier. Product size and weight are identified as key variables for shipping. Design drawings can be used to estimate these values, but a quality engineer instead randomly selects product samples from the assembly line to measure bracket length and weight. This data should help inform shipping carrier decisions. The data shown in the table on the right represents 11 samples from the line that were weighed and measured for overall length. The length measurements are recorded in inches to the nearest inch, and weight measurements are recorded in pounds to 2 decimal places. As an engineer learning about statistics, you naturally want the data to speak for itself. You put aside your assumptions or your preconceived ideas of what to expect and start asking questions of the data. You might consider asking questions like, How many samples are there? Is that enough? Okay, that's a simple one, of course, but sample size matters. More samples generally means more confidence in our analysis. You might ask, what numbers best describe this data? Some call these descriptive statistics. What is the range, or the maximum or minimum value? These help us understand variation in our sample. Is there a central tendency? Do we expect a certain value? How do length and weight relate? Physically, we'd expect a relationship between our key measurements. Are there any unusual measurements or outliers? Is there anything we don't expect in the data? Things that make us go, or that's odd. Of course, one of the first things we might do doesn't seem like statistics at all, but it is very relevant. Visualization. Some call this exploratory data analysis, or EDA. In this case, we make a scatter plot of length and weight. Visualizing data may help us get some early answers. It often leads to more questions. In this case, we generally see a positive trend between weight and length. There is noise or natural variation, but in general, we see higher weight for longer brackets. Good, that makes sense. Another type of visualization we use is a histogram. We'll get into the details later, but a histogram is a way of looking at the actual distribution of data. In this case, the sample size is small, but we do see the most weight between 6.8 and 8.2 pounds. That gives us some idea of the average or expected value. The fact that 3 of the 5 bins in the histogram have only 2 samples indicates some degree of uniformity in the data. The lowest occurring range of weight in the sample is between 5.4 and 6.8. This is somewhat informative, but we can't make concrete assessments with such a small sample. Interestingly, the sparse histogram visualization itself even helps us be cautious about drawing conclusions due to lack of data. To get a better idea of what our data is telling us, we'll start by calculating some simple descriptive statistics. We first look at the weight data, computing count, maximum, minimum, average, standard deviation, and variance. Count is the number of samples, a simple statistic calculated quite simply by counting the number of rows. Our sample has 11 values, so the count is 11. Now we don't yet know whether that's a high or a low number. If this is an early production test after preliminary automation setup, 11 could be all of the brackets we've ever made. In that case, it's the population. Once the process has volume comparable to the worldwide number of TVs sold, we could have thousands of brackets. In that case, 11 might be a small fraction of the total. Next, we'll look at max, min, and range. These are extremal values, so we'll need to order or sort our data. From top to bottom, we have the minimum to the maximum value, ordered 1 to 11. At the top, we see that the smallest value is 4.26 pounds. That's the minimum. The largest value at the bottom is 10.84 pounds. That's the maximum. The range is the difference between the largest and the smallest values, and it's a measure of the span or spread of the data. The range is defined R equals X max minus X min, where we're using X as a generic measurement variable. In this case, the range is 10.84 minus 4.26, which is 6.58 pounds. Sometimes we refer to this as the full-scale range or the full-scale output. The range is often used to normalize measurements as a relative percentage, taking the measurement value X, dividing by R, the range, multiplying times 100 to get a relative percent of a measurement value. We compute the mean by adding up all the values in the sample and dividing by the sample size n. The mean also has many names. It's also called the average, the arithmetic mean, the expected value, or sometimes just x bar, referring to the notation x as the variable being averaged and bar as the common notation over the x to represent the mean. For sufficiently large values of n, the sample mean approaches the population arithmetic mean mu. Whatever the name used, the mean is the most basic measure of central tendency in a distribution of data. In our sample of 11 weight measurements, on the right we add up each of the weight values. Their sum is 82.51. We divide by 11, the total count, n, and we get the mean, 7.50 pounds. This means that the average weight of each of the brackets sampled is about 7.5 pounds. A useful piece of information for our shipping decision about the TV brackets. It's helpful to plot the mean on the same scatter plot of the original weight versus length data. The mean, represented as a constant gray line in this plot, is 7.5 as previously computed. This visualization helps us see how much the measurements vary around the mean. Some are above and some are below, some are close to the mean and some are farther away. This gives us an idea of the relative variation in our data. The best way to quantify that variation in the measured value is to compute the sample variance and sample standard deviation. The sample variance is designated s to the second power, and the standard deviation is s. In order to compute the variance and standard deviation, we need the mean, x bar. To compute the variance, we take each value of x, the weight, minus the mean. We square that quantity, sum all of those values up, and then we divide by n, the number of samples, minus 1. To get the standard deviation, we simply take the square root of the variance. Note that we use n minus 1 in the divisor for a sample, where we use n for a population. The goal of calculating the standard deviation is to get a sense of the average distance from the average value. The step-by-step process to compute the standard deviation is as follows. First, calculate the sample mean, x bar. Then calculate the distance between each measure and the average. This is the, quote, deviation from the mean. Square each deviation, add up all the square deviations, and divide the sum by n minus 1, or n if using the population. Take the square root of the result, and the standard deviation then has the same units as the mean. This is helpful to visualize on the previous scatter plot, where the mean now is a black bar, constant across the plot, and one standard deviation measurement, plus or minus, is measured as the gray lines. Notice again the units of standard deviation and mean are the same. At this point, we've computed all of the common descriptive statistics of weight for our TV bracket sample. The sample count was 11. The average weight is 7.5 pounds and the standard deviation is 2.03, with the variance to square that 4.13. The max and min are 10.84 and 4.26 respectively. It's helpful to start looking at these numbers and trying to get an idea for what they tell us. For example, the average 7.5 plus about 1 standard deviation puts the range of typical bracket measurements between about 5.5 and 9.5 pounds. This gives us some intuition about the variation for our brackets that are manufactured on demand. Now we could compute the same type of statistics for length, but we'll leave that for another exercise, perhaps in a knowledge check. What we might first think about, though, is what is the relationship between length and weight? Can we quantify that in any way? We expect physically for there to be some logical connection between length and weight of our brackets. To get an idea of the relationship between length and weight, we need to model the relationship. We need to model the data. That type of model is sometimes considered an inferential statistical model. Linear regression, also known as least squares, is a process of fitting a simple linear model. The linear model has the form y equals a1 times x plus A naught. A1 and A naught are constants or parameters of the fit, A naught being the intercept and A1 being effectively the slope of the line. In this case, the slope is about 0.5, so it's roughly half of the weight is gained for every length measurement, and the intercept is 3.0. So the line doesn't go exactly through the origin at 0. And that's evident in the scatter plot. When we put that straight line as a trend line on the plot, we can see that general trend line is positive and up, but all of the data doesn't go exactly through that line. The way we measure the difference between that line and each of the data points is different for different applications, but a common measurement is called R squared. And R squared ranges from 0 to 1, where 1 is essentially a perfect model. In this case, we have an R squared of about 0.67. We don't have a good idea for exactly whether that's a good or bad fit, but generally it's what we would use in developing a model to fit our data. At this point, we should take a step back in our case study and remember what we're trying to do here, make a decision. Specifically, we're trying to make a data-driven decision about the shipping carrier that we'll use for our custom TV brackets. Generally, this process involves collecting data, converting it into information, usually through statistics, and then using those statistics to transform that information into knowledge and using the knowledge to make decisions. So for our TV brackets, well, the data is just sampled real consumer design brackets. We measure weight, we measure length. We have a total of 11 samples in our case. And hopefully those samples were randomly selected from the assembly line. The information or statistics that we can glean from that data are things like the length. The length ranges from 4 inches to 13 inch in 1 inch increments. The weight ranges from about 4 to 10 pounds, and the average weight is about 7.5 pounds. The standard deviation is 2 pounds, and we also see that there's a roughly linear relationship between length and weight. The relationship is linear of about 0.5 pounds for every 1 inch. So what does that tell us? Well, we have to transform those basic numbers into knowledge for decision making. One of the things we get from that is that bracket geometry varies, perhaps by design, since we allow customers to pick and choose some aspects of the design when specifying their own TV bracket. We also, from external information not represented in this data, gathered some information about the cost of shipping. And we can see for this geometry and weight specification that the shipping cost will range between $8 and $12 for each bracket, not a small number. We generally, of course, see that lighter materials will reduce our cost. Weight increases with length, but material cost is inverse to weight. We also should consider some other external information here about strength. Bracket strength could be a concern, especially since we're trying to hold up very expensive TVs. So what are we going to do? We're going to make a decision. And so after some research, including this type of analysis, we're going to choose shipping carrier UPEX, UPEX. We're also going to make the decision to limit the bracket size to 12 inch, and we're going to choose steel as the default bracket material, the best balance of cost, strength, and weight. At this point, we should think, what else could we gather in terms of information to help make this decision even more clear and better for our overall shipping process? With our preliminary sample and analysis, we take our decision to our boss. We recommend a shipping carrier, the specifications, and the material. And the boss comes back to us and says, "Are you sure? Is there anything else you can do to be more confident in your decision?" And the first thing we think of course, is to repeat the experiment, to sample more brackets. So we design a test where we collect 3 additional trials with the same format, 11 measurements sampled for length and weight for another set of brackets coming off the assembly line, perhaps on different days. We also want to compute the same kind of stats as before, count, average, standard deviation, variance, minimum, maximum, and do some regression analysis and compare those to our original data. We want to note similarities and differences for the statistics of each trial. Are the statistics the same? Is the data linear for each trial? Can we estimate the regression slope, intercept, and R-squared? How do the R-squareds compare? If we plot the data, how do they look? Can we comment on any observed patterns and really see if visualizing helps us with additional insight into this case? After a few days of collecting samples and measuring bracket length and weight, we tabulate our data and begin our statistical analysis. Again, we compute max, min, average, standard deviation, and variance for 11 samples. We look closely at the data and try to see any particular patterns. And we see something interesting. For the average and standard deviation and variance, we see oddly that all of the values are the same. 7.5 average, 2.03 standard deviation, and 4.13. This seems unusual, but it is a good indicator that our processes might be very consistent. We do see some variation in the max and the min weights, 10.84 and 4.26 from our original sample. The next one is slightly lower, 9.26 max and 3.1. The next one is slightly higher, 12.74 and 5.39. And then again, our last one is about 12.5 and 5.25. At this point, we're not looking closely at the length variable. The next thing we do with our 4 trials is to compute the regression statistics, slope, intercept, and R-squared. When we look at the trials 1, 2, 3, and 4, we see in the green box that the slope, intercept, and R-squared are actually all the same. 0.5, 3.0, 0.67, even though the weight variables, the weight measurements are different. Does this seem odd? We already saw some unusual consistency in average, standard deviation, and variance. And again, we see unusual, perhaps unexpected, slope, intercept, and R-squared consistency. We originally saw that the data had some rough noise or variation in it. So we're a little puzzled by this. What can we do? We decide to make another scatter plot, this time for all of the data from all 4 trials. We plot weight and length, and we again see some variation, but a generally positive linear trend between weight and length. We do see one unusual value up at the top right of the plot, but we don't quite know what to make of that. As before, we overlay a trend line over our data. In the scatter plot of weight versus length, the trend line is represented here, and it shows the linear regression equation 0.5x plus 3 with an R-squared of about 0.67. This is consistent with what we saw before for the individual trial. At about this point, we go back to our boss with our data and our analysis. We've done 4 more trials, and the statistics are pretty consistent as we look at them across all 4 trials, and our scatter plot shows a pretty strong case for a consistent linear trend between weight and length. It seems like we have a very consistent process and very consistent data to use for our shipping decision. Our boss asked us to look at one more thing. He asked us to look at error and uncertainty analysis and says, what type of scale did you use? What type of caliper did you use to measure the length? Obviously, the quality of the instruments could affect the numbers that we've measured. We take a look at the weight and we look at the scale, and the scale says that each measurement is about plus or minus 1% accurate. So we take that and we decide to plot error bars on our XY plot in the weight direction to give some sense of natural variation and uncertainty in each measurement. When we previously modeled the linear relationship between weight and length, we saw a very consistent straight line linear trend through the data. We used a linear regression with a slope and an offset, and we measured performance with an R-squared. The R-squared was 0.67. Even though the linear trend seemed like a good fit, our boss asks us, is that the best you can do? Is there a better model? Our statistical software allows us to explore other models, and one of the simple models that we can explore is a higher order polynomial. Instead of just x, we can look at x squared, x cubed, x fourth, x to the fifth, and even up to x to the sixth, a sixth order polynomial. When we run our regression process to find the parameters, the coefficients of this model, we get the line shown here. The equation is shown at the top of the plot. And to our expectations, this model with higher parameters performs a little better. We have an R-squared of 0.7, which is a pretty substantial improvement. The data in the plot look pretty consistent, except over on the far right, where our polynomial seems to take kind of a deep swoop down. The linear trend didn't do this, so we're a little skeptical about what this means. Does the data actually swoop down? We're not sure. Just to be sure our data makes sense, we take our analysis to a colleague and ask them to replicate it. The colleague makes a similar plot of our 4 trials, except this time the colleague chooses to put different colors and markers for each of the trials, and plots it in an XY plot, a scatter plot like we've seen before. As we look closer at this data, some things start to seem unusual and stand out. The yellow triangles all are clumped together in the middle around a length of 8. That's unusual. The green squares show an almost perfectly straight line, and the orange seems to have more of a curve, the orange circles. What's going on with this data? To visually explore this unusual trend that we see in our colored data, we decide to separate the plots out for each trial. We keep the scales the same range for our axes, and we decide to plot each of the different trials. On the top left, we have our original plot, our original data. The top right, our second trial. The bottom left is our third trial, and then the bottom right is our 4th trial data. Of course, the original data shows the roughly linear trend with random noise around that trend as we'd seen before. But we see some surprising results in the other trials. The second trial, even though the trend line goes through it, has the same exact regression parameters, the same exact average, standard deviation, and variance, it really looks much more closely like a parabolic or a quadratic equation. A linear fit just isn't a good model for this data. If we look at the third trial on the bottom left, we actually see, again, the trend line is the exact same for each of the other trials, but the trend line slope is actually a bit off from most of the data. 10 out of the 11 samples fit a perfect straight line, and it's just one sample, the second to the last one, that's way above the others. If we took that outlier out, we would actually see a different relationship, and almost perfectly linear, almost likely that our R-squared would be closer to 1. And then the last trial, the 4th trial, there just seems something amiss. Our length measurements are all about the same. It seems that our caliper is actually broken, and it's measuring 8 for every single trial and giving us random noise for the weight. This is only broken by a single point which shows up in the top right-hand corner. That single point takes that otherwise useless relationship and makes the straight line through it look exactly the same as all of our other trials. Same average, same standard deviation, Same variance, same intercept, same slope, and same r squared. This data, as shown here in these 4 trials, is actually from a classic statistical analysis paper. It's called Anscombe's quartet, and it's made up for this particular case study. It really illustrates some important concepts regarding visualization and data analysis. We'll get to those in the next slide. In looking at the sample bracket measurements and the unusual patterns that we discovered by separating the plots and showing how they all have different patterns, we actually are beginning to think about, well, how was the sample actually gathered? We'd like a random sample. Random sampling is essential to unbiased statistical analysis. With random sampling, the sample shouldn't differ in any systematic way from the population where it comes from. The Anscombe's quartet example is clearly fabricated for illustrative purposes and not actually randomly sampled. It's important to note that it is often impossible to account for all the things that you want to know about. A sample is a collection of separate observations of a variable, x, length, weight. It's a random sample when each observation is gathered independent of the others. A simple random sample size of n is a collection of n observations from the population that are all equally likely to have been selected. We typically list all of these observations like we did before in a sample with the variable x, x1, x2, x3, all the way to xn, such that x1 is the first observation and x2 is the second, and so on. Random sampling is key, but there are other systematic and non-random sampling strategies, such as stratified sampling. In stratified sampling, we intentionally gather a percentage of our samples from a subpopulation. Whatever the sampling strategy, the key is that our resulting sample is representative of the population in an intentional way. Otherwise, statistical results can be useless. To reiterate a few things about samples and sampling, one of the key points is that generally larger sample sizes, increase the confidence we have in the conclusion based on our statistics, only if the sample is random. The challenge is that taking more samples is often impractical or maybe even costly. We're again trying to avoid any mischaracterization of the population, also known as trying to avoid bias in our sample. We're always trying to collect randomly we can. It's really, really important to understand that it's actually impossible to use a sample to achieve absolute uncertainty about a population. Statistics is always about making the best possible estimate with the information that we have, never with absolute certainty. So this gets to a fundamental question of statistics: how to use samples to make confident statements about the entire population of our data. That concludes our introductory manufacturing case study. To reiterate a few points from this case study in the previous introduction, we should mention that a key point here is that manufacturing is changing. Statistics and data analysis skills are going to be critical for Industry 4.0. Some of these statistics don't have to be sophisticated. Simple statistics like mean, standard deviation, and count can be very helpful. And a really key point here is that statistics shouldn't be done in isolation without visualization. Visualizing our data, graphically presenting our data with appropriate plots and techniques allows us to augment our mathematical or statistical analysis to really make better decisions. We saw that quite clearly in the Anscombe's quartet example, where all the stats were telling us one story, but a simple visualization done the right way told an entirely different story. When we're working with data, we're working with samples most of the time, and sampling effectively helps us make confident decisions about populations. Again, statistics helps us make data-driven decisions.